What if what lies above and below our solar system changes everything we think we know? What if the familiar diagram we grew up seeing, the sun in the center, planets orbiting neatly around, a thin, flat disk slicing through the void, has always been a comforting lie? Not because the diagram is wrong, but because it hides the deeper truth. Our solar system does not float passively inside the Milky Way. It is suspended inside a vertical cosmic machinery, far more violent, far more dynamic, far more unpredictable than the simple picture suggests. Above us and below us are forces, structures, currents, and scars stretching across thousands of light years. They ignore the solar system's boundaries. They do not know we exist, but their hands reach down, quietly, invisibly, shaping our history, our future, and even our survival. Stand on Earth and look up. The sky appears calm, black, silent, unmoving. But this serenity is just the surface of a vast, three-dimensional storm. Our solar system is not embedded in a tranquil void. It is drifting through a galactic environment layered like an ocean, each layer hotter, stranger, and more unruly than the last. Above us is a realm of superheated plasma glowing in X-rays, sculpted by supermassive explosions millions of years old. Below us is a region shaped by dark matter currents, tidal distortions, and structures so large they wrap the entire galaxy like invisible rings. And in the middle, thin and fragile, we move along our orbital path around the Milky Way's center, ignorant passengers in a vessel floating through a multi-level cosmic atmosphere. To understand what lies above and below the solar system, we must first understand where we are. Not in the everyday sense, Earth, the sun, the planets, but in the galactic sense. Our solar system sits about 26,000 light-years from the center of the Milky Way, slightly above the galactic mid-plane. This height is small compared to the galaxy's full thickness, but it is enough to give us a unique vantage point. We hover just north of the dense ring of stars, gas, and dust that makes up the Milky Way's disk. If we could step back far enough to see the galaxy from the side, the sun would appear offset, like a grain of sand resting slightly above the surface of a spinning coin. But this position is not fixed. We oscillate. The sun moves up and down like a buoy riding slow-motion waves in a dark ocean. Each complete oscillation takes tens of millions of years, so slow that all of human history fits into a microscopic fraction of one vertical cycle. But these vertical movements are not harmless. The space above and below the galactic plane is not symmetrical. It is not empty, and the forces that shape it are not mild. Above the solar system lies a region sculpted by ancient violence. Giant bubbles of superheated gas inflate thousands of light years across. These bubbles are the ghostly fingerprints of events so energetic they reshaped the Milky Way's halo. They burst outward from the galactic center millions of years ago, when either a frenzy of star formation or a sudden feeding episode by the central supermassive black hole injected unimaginable energy into surrounding gas. The shock waves tore through the halo, heating it to over 2 million degrees. Even now, the remnants hang above us, like faintly glowing lanterns in a vast dark room. Their edges form colossal arcs, scar tissue marking the galaxy's violent past. Below the solar system lies a region influenced by structures of an entirely different kind. Structures that cannot be touched, cannot be seen, and yet exert more gravity than every star in the galaxy combined. Dark matter forms a halo enveloping the Milky Way like an invisible sphere. Smooth in some areas, turbulent in others, it contains rivers, clumps, filaments, shells, and possible caustic sheets where density spikes dramatically. We do not see them, but the solar system passes among them, sometimes grazing them, sometimes plunging directly through them, each encounter altering the weak, delicate gravitational environment surrounding the farthest reaches of our system. If dark matter clumps move like hidden currents, then the solar system drifts through a gravitational sea whose behavior we barely understand. Between these upper and lower dominions, the solar system carves a path that is anything but straight. It bobs, it weaves, it tilts. The Milky Way's gravitational field is not simple. It is shaped by the disk of stars, the central bulge, the dark matter halo, and even the passage of satellite galaxies swirling around us. The result is a gravitational landscape full of ridges, valleys, and shear zones. not unlike the turbulence an airplane feels when passing through shifting atmospheric layers. As we drift up and down through these forces, our cosmic neighborhood changes. The density of dust changes, the flux of cosmic rays changes, the pressure exerted on the heliosphere, the bubble of space shaped by the sun's solar wind, changes, and every change introduces a new risk or a new possibility. You might imagine the solar system as a ship. The sun emits a wind of charged particles that blow outward in all directions, forming a protective bubble around us. This is the heliosphere, our shield against much of the galaxy's radiation. But this bubble is not rigid. It shrinks and expands depending on the external pressure imposed by the interstellar medium above and below us. When we enter a denser region, the heliosphere compresses. When the environment thins out, the bubble expands. The structures above and below, the hot halo plasma, the dark matter tides, the magnetic fields threading the galaxy, push and pull on this bubble constantly. If the heliosphere shrinks too much, cosmic rays from outside the solar system penetrate more deeply, reaching Earth. They influence cloud formation, atmospheric chemistry, biological mutation rates, and possibly even climate cycles. If the solar system crosses a denser region of gas above or below the disk, the heliosphere could be squeezed to half or even a third of its current size. Some researchers have suggested that during extreme passages, Earth might be exposed to cosmic ray levels high enough to alter evolutionary trajectories. Not instant extinction, not radiation storms, but subtle, persistent changes that ripple across millions of years. And what about the Oort cloud, the vast spherical shell of icy bodies that surrounds the solar system? It extends halfway toward the next star. Its outer edge is so weakly bound to the sun that even small gravitational nudges can send comets spiraling inward. The structures above and below the solar system have the power to disturb these orbits. A passing dark matter clump, a region of stronger galactic tide, a vertical oscillation through a denser part of the disk, any one of these could increase the rate of comets falling toward the inner solar system. Not enough to doom us instantly, but enough to raise impact probabilities, enough to shape biological history, enough to occasionally rewrite the story of life. Consider this: every object above and every structure below the solar system is positioned along our vertical highway through the galaxy. These environments are layered like atmospheric shells, and each layer contains features capable of influencing the solar system in different ways. The hot halo plasma above us interacts with cosmic rays and magnetic fields, guiding particles in complex paths. The dark matter halo below us tugs on the Oort cloud. The galaxy's magnetic field, wrapping the disk like a twisted ribbon, fluctuates in strength depending on our vertical position. And massive structures, stellar streams, globular clusters, dwarf galaxies, wander through the halo like drifting islands, their gravity extending far beyond their halos of stars. We often think of the solar system as isolated, self-contained, untouched except by its own planets and asteroids. But the truth is the opposite. The solar system is a small system embedded in a much larger, constantly shifting environment. The forces above and below do not simply surround us, they shape our boundaries, push on our edges, and occasionally slip inside. The solar system is not merely orbiting the galaxy, it is immersed in it, molded by it, carried through it like a tiny spark drifting through a vast cosmic furnace. But there is something more unsettling, something deeper, something few people contemplate. Above and below the solar system lies geological time in physical form. Each layer, the hot gas, the dark matter sheets, the magnetic fields, the tidal peaks, represents a different epoch of galactic evolution. Some structures above us formed long before the sun existed. Some structures below us are remnants of galaxies devoured by the Milky Way billions of years ago. As we pass through them, we are not just moving through space, we are moving through the fossil record of the galaxy's violence. Imagine walking through a museum where every hallway represents a different era of destruction. Above you, a corridor filled with the still hot aftermath of dead stars. Below you, a corridor carved from invisible matter left behind by ancient collisions. And you, the Earth, humanity, walk unknowingly through these hallways, feeling faint tremors as each door we pass unlocks a new gravitational influence or a new cosmic pressure. Most of these effects are subtle, Some may be profound, but none are meaningless. All of this leads to a single, staggering question. What if everything we know about the solar system, its stability, its isolation, its predictability, depends on what lies above and below us, not just what orbits beside us? What if the true story of the solar system is not a story of 9 planets circling the sun, but a story of a fragile bubble drifting through a vertical labyrinth of forces far beyond our control? What if understanding these forces is not optional, but necessary if we hope to understand the past, the present, and the future of life on Earth? This is where the real journey begins. If we want to understand how what lies above and below the solar system could change everything we know, we must leave behind the comfortable, polished diagrams of science textbooks and instead imagine the galaxy as a layered, three-dimensional storm system, a place where invisible winds blow, where shock fronts drift for millions of years, where rivers of dark matter pass silently through space, and where our sun, so dominant in our local neighborhood, shrinks to the insignificance of a spark drifting through an immeasurable furnace. Above and below us exist realms that do not belong to the solar system. They belong to the galaxy itself. They are older than our star, harsher than our physics classrooms admit, and more chaotic than we have allowed ourselves to imagine. To begin to see their influence, picture the Milky Way not as a flat disk, but as a stacked world with multiple interacting layers. The midplane, where most stars are born, is a crowded, dusty zone lit by supernova explosions and stirred by spiral arms sweeping through in slow, majestic arcs. But rise above that plane, just a few hundred light years, and the scene changes dramatically. The density of stars plummets. Clouds of cool gas give way to diffuse streams of high-energy plasma. Magnetic fields, no longer tangled by the gravitational turmoil of the disk, stretch into longer, more organized shapes. Hot bubbles carved by ancient explosions swell outward like ghostly domes. And beyond those domes lies the halo, an enormous spherical reservoir of dark matter, faint stars, stellar debris, and relics of cosmic events long forgotten. This is the vertical architecture that surrounds us, and our solar system is not hovering quietly in the middle. It is moving through it, slowly, relentlessly. Every vertical oscillation through these layers exposes us to different pressures, different particle environments, different gravitational stresses. We are a ship rising and falling through a multi-level ocean we can barely measure. The first layer above us consists of hot ionized gas, plasma so diffuse that a cubic meter of it might contain only a handful of atoms, yet so hot that it glows in X-rays. This region is part of the galaxy's extended atmosphere, a feature astronomers once thought impossible. Galaxies were supposed to be mostly cold, dark structures surrounded by emptiness. Instead, we discovered enormous coronas of gas hotter than the surface of many stars, stretching hundreds of thousands of light years above and below the galactic disk. Our solar system resides near the inner boundary of this fiery expanse. Inside this layer, motions are slow but relentless. Gas heated by supernovae in the disk rises upward like a plume from a colossal volcanic eruption. As it expands, it cools slightly, but not enough to lose its identity as a million-degree plasma. Over millions of years, gravity eventually pulls some of it back down, creating a cycle reminiscent of a galactic weather system. This circulation is not symmetrical. Regions above and below the solar system do not match. Some areas contain large cavities carved by past explosions. Others hold denser pockets where gas accumulates and compresses. The boundaries between these regions form shock fronts, extending across distances measured not in light seconds or light hours, but in thousands of light years. The solar system drifts through this environment, inside its protective heliosphere. But even the heliosphere is not immune. Everything we travel through presses against it. Everything interacts. And when the pressure around the heliosphere changes, its size and shape change in response. A denser region of plasma above or below us can compress the heliosphere dramatically, allowing more cosmic rays from the galaxy to reach Earth. A thinner region allows it to inflate, granting the sun's influence a greater reach. These changes do not happen over days or months. They unfold over thousands of years, but their consequences accumulate slowly, like geological processes that shape continents grain by grain. now descend below the solar system, past the galactic midplane, into a region influenced more strongly by dark matter. Here, gravitational gradients shift in subtle ways. Dark matter, invisible but massive, surrounds the galaxy in a halo that extends far beyond the outermost stars. Yet this halo is not smooth. Simulations, and perhaps indirect evidence, suggest it contains substructures, cold streams created by the remnants of long-disrupted dwarf galaxies, clumps torn from the halos of objects devoured by the Milky Way, and thin caustic sheets where dark matter particles converge and momentarily increase in density. If the solar system passes near or through one of these structures, the gravitational pull on the outermost parts of the solar system, particularly the Oort cloud, could increase or decrease by small but significant amounts. The Oort cloud is the frontier where the sun's gravity fades into the galaxy's tide. Out there, at distances beyond 1 trillion kilometers, comets are held in place so weakly that forces 1,000 times weaker than Earth's gravity can nudge them into new orbits. A disturbance from above or below, a passing dark matter stream, a subtle increase in tidal pressure, a shift in the interstellar medium the solar system passes through could tilt the balance. A fraction of the Oort cloud might destabilize slightly, sending a small cascade of comets inward. If the cascade is large enough, the inner solar system experiences a period of elevated impacts. We see hints of such periods in Earth's geological record. We see craters whose ages cluster. We find chemical signatures in ancient rocks that hint at distant cosmic disruptions. But comets are not the only things influenced by the forces above and below. The galaxy's magnetic field also plays a crucial role. Threaded like twisted ropes, the field lines circle the disk in giant toroidal loops. They extend thousands of light years above and below the plane, shaping the movement of charged particles and guiding cosmic rays as they drift through space. Magnetic fields do not just sit and wait. They evolve. They twist, stretch, and reconnect. They create zones where cosmic rays accumulate and zones where they are depleted. Depending on our vertical position in the galaxy, the flux of high-energy particles entering the solar system can rise or fall. These fluctuations influence everything from atmospheric chemistry on Earth to the performance of spacecraft electronics. Above and below the solar system, the magnetic field is not uniform. It exhibits reversals, regions where the field points in the opposite direction. These reversals affect how cosmic rays propagate. If the solar system drifts into a region where the magnetic field is oriented differently, the cosmic ray environment around Earth could change noticeably. Not catastrophically, not apocalyptically, but measurably, enough to alter long-term climate patterns perhaps, enough to alter the mutation rate of life over geological timescales, enough to create subtle but persistent influences that ripple through the history of our planet. But the most dramatic structures above and below the solar system are the ancient bubbles blown by violent events near the galactic center. Millions of years ago, something happened at the Milky Way's core, something powerful enough to blast gas thousands of light years upward and downward. Astronomers debate whether this event was a burst of star formation or an episode of intense feeding by the supermassive black hole known as Sagittarius A. Whatever the cause, it left behind colossal bubbles of hot gas, now visible only in X-rays and gamma rays. The edges of these bubbles form enormous arcs stretching across vast distances, intersecting the halo and shaping its structure. The solar system is located far from these bubbles, but their influence extends outward in gravitational, magnetic, and energetic waves. Their shock fronts compress nearby gas. Their expanding shells alter magnetic field lines. Their interiors serve as reservoirs of high-energy particles that eventually leak outward. Over millions of years, as the solar system continues its vertical oscillation, it enters and leaves zones affected by these monumental structures. Each zone has different temperatures, densities, radiation levels, and cosmic ray intensities. The environment above and below us is not constant. It is layered and shifting. What does this mean for us? It means that the idea of a stable, unchanging cosmic environment is a myth. It means that biological and geological events on Earth could be influenced by processes unfolding far above and below the solar system. It means that the universe is not a static backdrop, but an active participant in the evolution of life. Consider the possibility that Earth's past environmental changes may have been nudged by cosmic forces. When the solar system crosses the galactic plane, something that happens roughly every 30 to 40 million years, the density of stars, gas and dust around us temporarily increases. Cosmic ray flux might increase as the heliosphere is compressed. Impact rates might rise as the Oort cloud is perturbed. These ideas are debated, not proven, but patterns in Earth's fossil record hint at cycles. Extinction events appear to cluster in rough intervals. Geological layers preserve signs of cosmic disturbances. The timing is not perfect. The evidence is not definitive, but the idea is haunting. What lies above and below us may have shaped the story of life. We tend to imagine the solar system as a safe harbor, a place defined by its internal dynamics, planetary orbits, asteroid belts, solar cycles. But the truth is far broader. The solar system is an island drifting through a cosmic archipelago of invisible forces and ancient scars. The structures above us are the remnants of past violence. The structures below us are the frameworks of unseen matter that hold the galaxy together. And our journey through them is continuous, inevitable, and far more consequential than we once believed. If what lies above and below the solar system changes, then everything changes. The size of our protective bubble, the rate of impacts from space, the background radiation bathing our atmosphere, the long-term stability of Earth's climate, the very history of life crawling across the continents. We do not live in an isolated system. We live in a corridor of forces we barely understand. A corridor that extends not just horizontally across the galaxy, but vertically across its hidden layers. And this is only the beginning. If we look above and below our solar system with the right eyes, not the eyes of biology, but the eyes of astrophysics, we begin to see that the space surrounding us is not empty at all. It is layered, structured, scarred, and deeply alive with motion. It behaves less like a placid void and more like a dynamic ocean whose currents, tides, and storms operate on scales so enormous that our entire civilization is a fleeting whisper inside their cycles. To understand how these vertical realms might shape everything we know, we must leave behind the idea of space as a silent backdrop and instead embrace the unsettling truth. The galaxy has weather, and we are moving through it. Consider first the boundary that defines where the solar system ends and the galaxy begins, the heliopause. This is not a fixed border, but a membrane, a tension point between the outward pressure of the solar wind and the inward pressure of the interstellar medium. The cosmic environment above and below us pushes on this membrane constantly. The heliosphere is like a balloon drifting through a series of invisible atmospheric layers. Each layer squeezes the balloon differently. Each layer changes its shape, and each layer affects what gets inside. Voyager 1 and Voyager 2, the two oldest functioning robotic explorers ever launched by humanity, have tasted these outer regions firsthand. Their instruments recorded the moment they crossed the heliopause, not as a sharp boundary, but as a transition zone where particles and magnetic fields shifted subtly, like stepping from soft sand into water. Above and below that membrane lies the interstellar medium, a realm shaped by ancient shocks, tenuous gas, and cosmic rays accelerated over distances we can barely visualize. This environment is not static. It varies depending on the structures that fill it, and many of those structures originate in the regions above and below the galactic plane. One of the most significant features shaping these layers is the local bubble, a colossal cavern-like void carved into the galaxy's disk. The solar system is inside this cavity. Its walls are formed from shells of gas pushed outward by multiple supernova explosions. The space inside is filled with hot, thin plasma that glows faintly in X-rays. But this bubble is not symmetric. Its northern and southern halves differ in temperature, density, and shape. These differences likely influence the pressure exerted on the heliosphere. Above the solar system, the local bubble expands into a region where the density drops sharply, connecting to larger cavities in the galactic disk. Below us, the bubble's boundary thickens as it merges with adjacent structures sculpted by older explosions. These differing conditions mean that the Sun travels through an environment where the forces pressing against the heliosphere are not evenly distributed. When the northern region is hotter, it pushes harder. When the southern region contains cooler, denser gas, it pushes differently. These asymmetries create fluctuations in the heliosphere's structure. They change how much galactic radiation penetrates inward. They reshape the cosmic ray landscape surrounding Earth. But the local bubble is only one layer. Beyond its boundaries, above and below the plane, lies the galaxy's hot halo, a massive envelope of ionized gas extending hundreds of thousands of light years into space. This halo contains temperatures reaching 1 to 2 million degrees Kelvin, far exceeding the heat of the sun's corona. Yet its density is so low that a human could travel through it without feeling a thing. This plasma, heated by supernova explosions and gravitational compression, conducts electricity and interacts with magnetic fields across vast distances. These interactions generate turbulence, waves, and shocks, galactic-scale weather patterns whose influence stretches far beyond their points of origin. As the solar system moves vertically, it may pass closer to or farther from denser regions of this halo. These regions can increase the drag on fast-moving clouds of gas, redirecting their paths. They can alter the magnetic field lines that cosmic rays follow. They can compress or distort the outer layers of the heliosphere. For Earth, the effects are not immediate, but cumulative. Over geological timescales, changes in cosmic ray flux caused by variations in the surrounding halo environment could subtly influence cloud formation. Higher cosmic ray flux produces more atmospheric ionization, which some scientists believe can seed cloud droplets. More clouds could cool the climate. Fewer clouds could warm it. Over millions of years, even slight shifts might have shaped climate cycles long before humans had words to describe them. If the halo above is a plasma ocean, the region below us is a gravitational ocean, dominated not by hot gas, but by dark matter. This invisible mass generates the majority of the galaxy's gravity. It shapes the orbits of stars. It forms the scaffolding around which galaxies assemble, and it does not lie quietly. The dark matter halo contains substructures that drift like ghostly continents and rivers. Some are remnants of ancient dwarf galaxies torn apart by the Milky Way. Some may be long, thin streams formed when dark matter particles fell into the galaxy along filamentary pathways billions of years ago. Some may be dense, caustic layers, regions where particle trajectories converge, increasing density sharply. These structures exert gravitational pull on everything they pass. They do not grab hold of the solar system directly, not in a way we could detect with a spacecraft or telescope, but they influence the farthest edges of the sun's domain. The Oort cloud, containing perhaps trillions of icy bodies, is so far away that even tiny changes in gravitational forces can reshape orbits. If a dark matter clump passed beneath or above the solar system, its gravity could push on the Oort cloud unevenly. The result might be an uptick in comets falling inward, a faint but noticeable shower that could last hundreds of thousands of years. Some scientists have proposed that dark matter interactions might leave signatures in the crater records of planets or moons. Others suggest they might occasionally trigger subtle patterns in Earth's mass extinction timeline. But gravitational tides from dark matter are not the only vertical forces at play. Above and below the solar system flow stellar streams, long, thin ribbons of stars torn from disrupted dwarf galaxies and globular clusters. These streams move through the halo like tendrils of scattered glass. Their stars follow similar orbits, weaving through the galaxy's gravitational field in predictable arcs. Although they are extremely diffuse, their combined mass is significant. Each stream slightly warps the gravitational landscape, like a submerged current altering the motion of a drifting ship. As the solar system rises and falls through the galaxy, it crosses the orbital paths of these stellar streams. Their gravitational influence is gentle but persistent. Over millions of years, they contribute to the cumulative forces shaping the motions of the Oort cloud. Now imagine the solar system millions of years from now. It drifts into a region where a stellar stream passes just above it. The combined influence of the stream and the local dark matter distribution slightly increases the tidal forces on the Oort cloud's outer edge. Comets that once orbited steadily may begin to drift. Some fall inward, most do nothing at all, but a few become gravitational dominoes, small nudges that create long-term cascades. Over tens of millions of years, these small nudges accumulate, creating patterns in cometary activity that ripple into the inner solar system. This concept challenges the idea that Earth is shaped only by internal forces, volcanoes, plate tectonics, climate cycles, biological evolution. Instead, it suggests a richer, more complex story. Earth's history might be entangled with vertical motions through the galaxy's layered environment. Above and below the solar system lie magnetic structures too large to comprehend. The galaxy's magnetic field is not simple. It wraps around the Milky Way like two colossal toroids, one above, one below. Their orientations differ, their strengths vary. Their origins come from the rotation of ionized gas combined with convection currents that stir deep within the disk. These dynamo-like processes create magnetic fields that twist, flip, and meander across thousands of light years. As the solar system moves through these regions, the magnetic field strength changes. Cosmic rays, sensitive to magnetic fields, alter their paths accordingly. More cosmic rays reach Earth during some vertical phases, fewer during others. Above us, some regions act like magnetic lenses, focusing cosmic rays inward. Below us, others act like magnetic shields, deflecting cosmic rays away. These zones shift over time. They might thicken, thin, or drift through the halo. When the solar system passes through them, the cosmic ray environment changes with slow, rhythmic patterns written into geological history. And then there are the bubbles, the colossal, near-spherical shock fronts created by ancient eruptions in the galactic center. These are the scars of the galaxy's past. They tower above and below the plane like ghostly monuments. They extend thousands of light years, dwarfing the solar system beyond imagination. Within these bubbles, temperatures soar. Magnetic fields stretch. Cosmic rays swirl in turbulent vortices. Although the solar system is far from the core, the shock waves from these ancient events continue to shape the halo environment. Their edges compress gas, alter field lines, and potentially influence the regions the solar system eventually passes through. Imagine the solar system drifting upward through the galaxy over millions of years, rising like dust, carried by a cosmic breeze. Eventually, the heliosphere enters a region where the influence of one of these ancient shock fronts still lingers. The magnetic environment changes subtly. Cosmic ray intensities shift. The heliosphere adjusts its boundaries. The Oort cloud feels faint ripples in gravitational potential. Earth, insulated by atmosphere and magnetosphere, notices none of this in daily life. But fossils, climate records, and geological signatures might tell the tale millions of years later. The deeper we look above and below us, the more we realize that all these forces, dark matter, halo gas, magnetic fields, stellar streams, shock fronts, and vertical oscillations, form a single interconnected system. Together, they define the environment through which the solar system moves. Together, they shape what enters our heliosphere. Together, they influence the long-term stability of comets, the cosmic rays reaching Earth, and even the evolution of life. Above and below us lie the engines of galactic weather, and we are drifting through their storms. To grasp how what lies above and below our solar system could reshape everything we think we know about Earth, about the Sun, about the galaxy itself, we must confront a truth that is both unsettling and strangely poetic. The solar system is drifting through a universe that is not flat, nor uniform, nor passively empty. It is layered like a colossal atmospheric stack, each layer containing structures and forces that dwarf our imagination. And as we rise and fall through these layers, we are not merely passengers in a cosmic elevator. We are participants in an ancient dance whose steps were choreographed long before our star ignited. To understand this dance, imagine the galaxy as a multidimensional machine, a machine that runs on gravity, magnetism, plasma flows, supernova shockwaves, and the silent architecture of dark matter. Nothing inside this machine is static. Nothing is still. The Milky Way pulses and circulates. Gas rises and falls. Magnetic fields twist like coiled serpents. The halo churns with million-degree turbulence. Stars orbit in layered highways. Streams of stellar debris drift like ghostly rivers. And the solar system, our fragile home, is swept along paths determined by these colossal structures. Above the solar system stretches an expanse shaped by the aftermath of ancient violence, a realm where superheated gas fills cavities blown open by explosions that occurred millions of years before humans existed. These cavities, sometimes thousands of light years across, form a patchwork of interconnected voids. The local bubble, our bubble, is only one piece of this sprawling network. Its boundaries are rough, its edges are fractured. It connects to adjacent bubbles, making the galactic disk look less like a neat, thin layer of stars and more like a block of Swiss cheese, riddled with tunnels carved by dead suns. But the northern direction, above the solar system's current position, is especially scarred. There, shock-heated plasma forms a corridor stretching upward into the galaxy's halo. Temperatures rise into the millions of degrees. Density drops to levels so thin, it is nearly the closest thing to nothingness the universe can achieve, while still containing matter. Yet within this nothingness, magnetic fields cling to shape. Shock fronts persist. Remnants of supernovae merge with older structures, creating gradients in pressure that ripple outward through the halo. These gradients influence the solar system indirectly but persistently. When they are strong, they increase the compression of the heliosphere. When they weaken, the heliosphere expands. Even slight changes can alter the cosmic ray flux reaching Earth. During periods when the heliosphere is swollen, Earth enjoys enhanced protection. Fewer cosmic rays reach the atmosphere, fewer high-energy particles strike the surface, and the ionization rate in the upper atmosphere declines. But when the heliosphere shrinks, cosmic rays surge inward. They break apart molecules in the atmosphere. They alter the chemistry of clouds. They influence long-term climate. These patterns may be slow, but they are not trivial. Over the course of tens of millions of years, a fluctuating cosmic ray environment could leave fingerprints in Earth's geological and biological history. Fingerprints that might be misinterpreted if we assume the solar system's environment has always been constant. Now descend below the solar system, past the galactic midplane, where the density of stars increases. This region is where most of the galaxy's mass is concentrated. It is where star formation thrives. It is where gas clouds churn and collide. It is where spiral arms sweep through like gravitational tides, compressing gas and igniting new stars in waves that travel across the disk on timescales longer than life itself. But the further we fall below the plane, the more the galaxy reveals its oldest layers, regions dominated not by new stars, but by ancient structures preserved from earlier eras of galactic evolution. These include the thick disk, a population of older stars orbiting the galaxy with higher velocities and greater vertical dispersion than the stars in the thin disk. Some of these stars were born here. Others were captured from dwarf galaxies that merged with the Milky Way long ago. Their orbits are tilted. Their trajectories cross the plane at sharp angles. Their distribution holds clues about past collisions that reshaped the galaxy and left scars still visible in the motions of stars today. Below this lies the stellar halo, a vast cloud of ancient stars extending far above and below the disk. Their motions are chaotic. Their orbits are elongated. They pass near the galactic center and then swing far out into the void. This population holds relics of every major merger the Milky Way has experienced. When we look at the halo, we are looking at the fossil record of the galaxy's most violent ages. These halo stars, though faint and sparse, help map the gravitational field below us. They move according to the contours of the underlying dark matter halo. Their motions reveal that the dark matter below the plane is not evenly distributed. It contains ripples, dips, clumps, and ridges. These features are relics of ancient dwarf galaxies that were torn apart, their stars flung outward while their dark matter cores dissolved into the halo. Each merger changed the gravitational environment of the galaxy. Each merger subtly reshaped the vertical forces the solar system experiences as it oscillates up and down. Cosmologists have discovered that the Milky Way contains at least one major surviving stream of dark matter, known as the Gaia sausage, or Gaia Enceladus, the remnant of a dwarf galaxy that collided with the Milky Way billions of years ago. This collision not only added stars to the halo, but also deposited dark matter into a highly elongated structure aligned roughly perpendicular to the disk. If the solar system passes near regions where this structure influences the local gravitational field, the Oort cloud could experience subtle but significant perturbations. The Oort cloud itself is an astonishing structure, a sphere of icy debris so large it defies comprehension. These comets do not orbit the sun like planets. They drift, barely bound by solar gravity. existing in a liminal state between membership in the solar system and capture by the galaxy. The galactic tide, the combined gravitational influence of the disk and halo, determines their fate. When the solar system moves upward or downward, the direction and strength of this tide changes. It squeezes the Oort cloud in some directions and stretches it in others. This stretching and squeezing do not create immediate chaos. They produce slow drift, gradual instabilities, tiny changes in orbital energy that may take millions of years to accumulate, yet the consequences can be enormous. A slight nudge in the outer Oort cloud can send a comet inward. Most pose no danger, but some do. Cometary impacts have reshaped Earth's past, triggered extinction events, and delivered water and organic compounds that may have seeded life itself. If what lies above and below the solar system influences the Oort cloud, then it influences the history of life on Earth. But the influence of vertical structures goes beyond comets and cosmic rays. It extends into the very organization of the galaxy's magnetic fields. These fields are not simple lines threading the disk. They are vast toroidal loops above and below the plane. They rotate with the galaxy. They twist with differential rotation. They shift when supernovae erupt. They stretch during interactions with satellite galaxies. And like Earth's magnetic field, they may undergo reversals on timescales of hundreds of millions of years. These reversals change how cosmic rays move. They change how charged particles drift. They change the magnetic shielding of the solar system at different altitudes above and below the plane. They create zones where magnetic fields act like lenses, focusing cosmic rays inward. They create zones where cosmic rays are deflected outward, leaving Earth in a relative lull of radiation. Above and below us, the magnetic environment is not a smooth gradient. It contains sheets, folds, and abrupt transitions. Some are boundaries between regions of different magnetic polarity. Others are the edges of supershells carved by supernovae. When the solar system crosses one of these transitions, the behavior of cosmic rays changes abruptly. The heliosphere's shape changes. The interface between solar and interstellar magnetic fields twists into new configurations. Even more dramatic are the structures known as Parker instabilities. These are buoyant magnetic loops that rise above the galactic plane like enormous arches. They form when magnetic field lines in the disk become tangled and rise upward due to buoyancy forces. Gas flows along these arches, creating currents that move vertically across the galaxy. The solar system may drift through some of these magnetic arches. Their influence is subtle but real. They alter the cosmic ray environment and potentially the density of the interstellar medium we encounter. And then there are the superbubbles, massive cavities created by clusters of supernovae. They expand upward and downward, carving chimneys that allow hot gas to vent into the halo. These chimneys connect the disk to the halo like enormous breathing tubes, carrying metal-rich plasma upward and drawing cooler gas downward. If the solar system ever passes near one of these chimneys, the interstellar medium around us could change dramatically. Gas density could increase. Magnetic fields could intensify. Shock fronts could ripple outward into regions the solar system eventually occupies. What does all this mean for us? It means the solar system exists inside a three-dimensional labyrinth of forces. Forces that stretch across thousands of light years and evolve over millions of years. It means that Earth's history is not written only by terrestrial events, but also by cosmic currents flowing above and below us. It means that to understand the solar system's true nature, we must think vertically, not just horizontally. Above us lie the scars of ancient explosions. Below us lie the relics of galactic collisions, and we are drifting between them, carried by gravity, swept by tides, influenced by magnetic fields, and surrounded by millions of degrees of superheated plasma. Above and below the solar system lies everything the textbooks never taught us, everything we are only beginning to understand. If we want to understand why what lies above and below our solar system could change everything we know, we must travel deeper into the realms that surround us, regions shaped not only by gravity, magnetic fields and supernova debris, but also by the broader architecture of galactic evolution. This architecture is not rigid. It is fluid, alive, sculpted by tides of matter and energy that have flowed for billions of years. And as the solar system drifts up and down through the Milky Way, it encounters different layers of this architecture, each one with properties capable of influencing Earth in ways subtle or profound. The first layer we encounter when rising above or falling below the disk is the transitional zone, where the thin disk gradually fades into the thick disk. The density of stars drops, gas becomes more diffuse, molecular clouds become rare, star formation dwindles. But this region is not empty. It hosts the remnants of older stellar populations, stars that formed during epochs when the Milky Way was more chaotic, when mergers were common and the disk was still settling. Some of these stars move in arcs inclined steeply relative to the disk. Others plunge through the plane at high speeds, like stones skipping across a cosmic pond. Their motions tell us that the thick disk is a relic of a turbulent past, perhaps shaped by ancient collisions that heated and stirred the stellar population. When the solar system oscillates vertically through this region, it moves through gravitational fields shaped by these older stars. Their distribution affects the galactic tide pulling on the Oort cloud. Their density influences the frequency of close stellar encounters, and their interactions with the gas and magnetic fields around them create currents that ripple into the halo above. Beyond the thick disk lies the inner halo, a region dominated by ancient stars arranged in a roughly spherical distribution. These stars are among the oldest in the galaxy, forming at a time when the Milky Way had not yet acquired its familiar spiral structure. Their chemical fingerprints are distinct. They contain fewer heavy elements, because those elements had not yet been produced by generations of supernova. Each star is a fossil of a time before the galaxy settled into order. As the solar system rises into this inner halo, the density of stars continues to drop, but the diversity of orbits increases dramatically. Some stars move in long radial paths that plunge them toward the galactic center before carrying them back into the halo. Others follow wide loops that stretch thousands of light years above or below the disk. Their motions create a complex gravitational tapestry. Every oscillation of the solar system through this region is influenced by the collective pull of these stars, each one contributing a small but measurable effect to the overall galactic tide. And then there are the relic streams, long ribbons of stars left behind by dwarf galaxies that fell into the Milky Way and were torn apart. These streams wrap around the galaxy in intricate patterns, crossing the halo at angles that cut through the vertical axis of the disk. The solar system may occasionally pass near these streams, and when it does, the gravitational environment shifts subtly. Some streams possess denser clumps, where the original galaxy's core resisted tidal disruption. These clumps can behave like invisible lenses, bending the orbits of comets in the Oort cloud, or altering the solar system's path through the galaxy by minute yet cumulative amounts. Rising further above the disk, we encounter the hot halo, a gargantuan sphere of million-degree plasma extending hundreds of thousands of light years in every direction. Though incredibly diffuse, this plasma carries enormous energy. It emits X-rays that can only be detected by space-based telescopes. Its temperature is so high that atoms are stripped of electrons, creating a soup of ions and magnetic turbulence. If the solar system travels deeper into this halo, the heliosphere compresses as it pushes against the higher pressure environment. A compressed heliosphere offers less protection against cosmic rays. Even small reductions in size can significantly alter the flux of particles reaching Earth's atmosphere. Over geological time, such changes may leave signatures in isotopic ratios, climate shifts, or biological patterns. Scientists have long debated whether increases in cosmic ray flux could influence cloud formation, atmospheric chemistry, or even mutation rates in living organisms. If the solar system's vertical motion transports it into hotter or denser regions of the halo, the cosmic ray environment could change enough to affect Earth on evolutionary timescales. But the hot halo itself is shaped by deeper forces. Supernova explosions in the disk launch gas upward, forming plumes that rise like cosmic geysers. These plumes expand, cool, fracture, and blend into the halo, bringing metals forged in stars into regions far above the plane. At the same time, gas from the intergalactic medium falls inward, heating as it plunges into the Milky Way's gravitational well. These inflows and outflows create circulation patterns, vast convection currents spanning tens of thousands of light years. The solar system's position relative to these flows matters. If it drifts into a region where hot gas is streaming upward, the local pressure around the heliosphere may rise. If it drifts into a region where gas is cooling and falling, the pressure may drop. Pressure gradients shape magnetic fields. They influence the distribution of dust. They alter how cosmic rays propagate. And they may even contribute to long-term cycles that shape Earth's exposure to interstellar matter. Beyond the hot halo lies the dark matter halo, an even larger and more mysterious structure. It is invisible, yet it provides the majority of the galaxy's gravitational pull. Dark matter determines how stars orbit. It determines the shape of spiral arms. It determines the Milky Way's rotation curve. It forms clumps, filaments, and shells. Some of these structures extend thousands of light years above the disk. The solar system is constantly moving through dark matter. Billions of particles pass through each human body every second. Though these particles rarely interact with ordinary matter, their collective mass influences everything. Vertical motion through the dark matter halo exposes the solar system to regions of varying density. A slight increase in local dark matter density enhances the galactic tide pulling on the Oort cloud. A decrease weakens it. The distribution of dark matter is not smooth. It contains subhalos, small concentrations left over from ancient cosmic structure formation. Passing near a subhalo could subtly perturb the solar system's orbit or alter the orientation of comet reservoirs. Dark matter streams, produced by the remnants of long-vanished dwarf galaxies, weave through the halo like invisible rivers. If the solar system moves through one of these streams, the local gravitational field could shift for tens of thousands of years. The vertical oscillation itself is shaped by these structures. It is not a simple harmonic up and down motion. It is influenced by clumpy distributions of mass, asymmetric density gradients, and dynamic processes such as mergers and stellar feedback. Some models suggest that the solar system's oscillation may have changed over time, with periods of stronger or weaker vertical displacement depending on the mass distribution of the Milky Way at different epochs. This leads to a profound question. Could Earth's long-term cycles, geological, biological, or climatic, be influenced by the solar system's vertical journey? Some researchers have proposed correlations between mass extinction events and periods when the solar system crosses the galactic plane. Others have noted possible alignments between biodiversity cycles and oscillations through regions of varying cosmic ray density. These ideas are controversial, but they highlight a crucial point. The environment above and below the solar system may play a role in shaping life on Earth. If the solar system passes through regions with enhanced cosmic rays, mutation rates could increase. If it passes through denser clouds of interstellar gas, the heliosphere could compress dramatically, exposing Earth to higher radiation levels. If the galactic tide becomes stronger, the Oort cloud could release more comets, raising the frequency of distant impacts. If the dark matter density increases, exotic interactions, still hypothetical, could influence planetary atmospheres or internal heat flows. Even our models of the galaxy itself could be challenged. If the structures above and below us prove more dynamic, more massive, or more complex than expected, our understanding of how galaxies evolve would require revision. The solar system's humble vertical motion becomes a diagnostic tool, a probe traveling through a cross-section of galactic history, sampling the layers of the Milky Way like a spacecraft descending through the atmosphere of a planet. Above and below us lies everything that shaped the galaxy before the sun was born. Everything that influenced the birth of stars, everything that determined the flow of matter from the disk into the halo, everything that defines the inner architecture of the Milky Way. And as we drift through these layers, we are not simply observers, we are pieces of the system, bound to it, carried by it, influenced by it. Whether we rise into the halo or fall toward the plane, one truth remains. The galaxy is not the calm, flat disk of childhood textbooks. It is a vertical labyrinth of forces and structures, each one capable of altering the future of our solar system and the history of life on Earth. If we dare to ask how what lies above and below our solar system could change everything we know, then we must confront a reality even more surprising than the hot halo, the magnetic arches, the Oort cloud, or the dark matter streams. Because the farther we investigate, the more we discover that the space the solar system moves through is not a backdrop. It is a living environment, active, structured, and capable of leaving imprints across millions of years of planetary history. To understand this fully, imagine the solar system not as a solitary island drifting through emptiness, but as a ship navigating a vast, multi-layered ocean. Above and below this ocean's surface lie currents that flow in every direction. Some are slow, some fast, some turbulent, some smooth. The ship does not travel through one static environment for the entire journey. Instead, it passes through regions with different densities, temperatures, magnetic fields, radiation levels, and gravitational distortions. Some regions nurture the ship, others threaten it. Some leave no visible trace, others produce consequences that may take millions of years to manifest. Astronomers once believed that the interstellar medium, the matter between the stars, was nearly uniform. That belief collapsed as better telescopes revealed a chaotic ecosystem of clouds, bubbles, filaments, and shock fronts. Today, we know that the solar system's surroundings can change dramatically over distances of a few dozen light years. And though these distances sound vast to us, they are small on galactic scales. The solar system's orbital speed through the galaxy ensures that we drift into new interstellar environments regularly on geological timeframes. Consider the interstellar clouds themselves. Not all are dense enough to affect the solar system. Most are thin, wispy structures that pose no threat and barely influence the heliosphere. But some, especially the so-called cold, neutral medium clouds, can be thousands of times denser than the average interstellar gas. If the solar system encounters one of these clouds, the consequences could be profound. A cloud dense enough would compress the heliosphere dramatically, perhaps shrinking it closer than the orbit of Saturn. In such a scenario, the solar system's planets would be exposed directly to interstellar particles. Cosmic rays would surge inward unchecked. The sun's magnetic shield would weaken. Earth's atmosphere could be altered by increased ionization. Ozone levels might fluctuate. The climate might shift. And over tens of thousands of years, these subtle changes could accumulate, reshaping the environmental conditions on Earth or any future human habitats. Above and below the solar system lies an intricate series of such interstellar clouds, arranged like layers in a shifting, turbulent ocean. Some are remnants of long-dead stars. Others are part of larger complexes. Some drift as isolated patches of cold gas. Others ride along in enormous flows generated by spiral arm shock waves or supernovae explosions. As the solar system moves vertically through the galaxy, it does not remain locked in a single stable interstellar environment. It migrates through these clusters of clouds, each with its own density, temperature, and magnetic signature. Our current home, the local interstellar cloud, is relatively benign. It is warm, somewhat diffuse, and stable. But maps of the region above and below us show that the solar system is moving slowly toward the edge of this cloud. Beyond it lie other clouds, some denser, some thinner. Some may confine the heliosphere, others may allow it to expand. The direction of our travel matters. If the solar system continues its drift upward out of the galactic plane, the distribution of clouds changes. There are regions above the plane where the interstellar medium becomes thinner and hotter. There are also patches where small dense clouds linger like cosmic reefs, waiting silently in the dark. These clouds are not the only features that make the vertical axis of the galaxy so dynamic. There are also shock fronts, expanding shells of gas from ancient supernovae. Many are faint and difficult to detect, but they exist. They sweep through the galaxy like tidal waves of ionized plasma, propagating slowly over millions of years. If the solar system encounters such a shock front, the heliosphere would again be compressed. The radiation environment would intensify. The interstellar magnetic field would change abruptly. Even the influx of interstellar dust could increase. Dust, though minuscule, has significant influence. Tiny grains can drift into the solar system when the heliosphere weakens. They accumulate in the inner planets. They affect atmospheric chemistry. They interact with Earth's climate subtly, but continuously. During times when the solar system moves through regions richer in interstellar dust, the inflow of grains increases, and these particles contribute to long-term changes in atmospheric transparency or global temperatures. Over thousands of years, such changes could imprint predictable or chaotic variations into Earth's natural climate cycles. Above and below us lie reservoirs of such dust. Some are relics of past galactic mergers. Others are debris left behind by star formation regions long dissolved. Still others drift in from the intergalactic medium, carried inward by the gravitational pull of the Milky Way. The vertical distribution of dust is not symmetrical. Cosmologists have discovered that dust layers in the halo tend to form subtle gradients, thickening in some regions, dissipating in others. These gradients may act as cosmic seasons, influencing how much dust enters the solar system over long intervals. Another factor becomes relevant as we move further above or below the disk: the galactic magnetic field. The field in the disk is heavily influenced by the rotation of the galaxy, turbulence in molecular clouds, and the remnants of supernovae. But above and below the disk, the field is not anchored by the same structures. It becomes more vertical, more diffuse, and often more coherent. Magnetic field lines stretch upward into the halo, forming loops and arcs that resemble enormous cosmic highways. The solar system interacts with these fields constantly. As we drift through different regions, the orientation, strength, and coherence of the magnetic field changes. These changes affect the heliosphere's shape. They alter how charged particles propagate. They influence the shielding effect of the sun's wind, and they determine how cosmic rays spiral onto Earth's poles. Vertical structures in the magnetic field can create zones where cosmic rays are funneled inward more efficiently, enhancing radiation levels even when the heliosphere is strong. Other zones deflect cosmic rays, creating temporary reprieves. If future civilizations hope to understand Earth's long-term radiation environment, they must understand this magnetic scaffolding above and below the disk. But the vertical axis of the galaxy also contains another phenomenon, one far less intuitive but equally important: gravitational waves from galactic-scale interactions. Not the space-time ripples detected by LIGO from merging black holes, but subtle, persistent oscillations in the distribution of matter caused by past galactic collisions. These oscillations ripple through the halo, altering the density of stars and dark matter above and below the disk. Some scientists believe the Milky Way's disk itself is still vibrating from ancient impacts, moving up and down like a struck gong. If this is true, then the solar system's vertical motion is not a simple orbit. It is superimposed on a larger dynamical oscillation of the entire disk. These oscillations could alter the solar system's path over hundreds of millions of years, changing the timing and amplitude of its vertical displacement. Such shifts could influence how often we pass through dust layers, magnetic structures, dark matter streams, or interstellar clouds. Traveling downward below the plane, the distribution of structures changes once again. The southern side of the Milky Way appears subtly different. Some shock fronts are more prominent. Some large-scale bubbles are less symmetrical. Some magnetic loops appear twisted relative to their northern counterparts. These asymmetries may be relics of past events, supernovae that erupted more strongly in one hemisphere, or dwarf galaxies that merged preferentially on one side of the disk. Even the tilt of the dark matter halo relative to the disk may not be symmetrical above and below. If the halo is misaligned, its gravitational pull changes differently depending on vertical direction. That means the solar system could encounter different tidal environments depending on whether it oscillates upward or downward. This matters for the Oort cloud. A slightly stronger tidal field can destabilize cometary orbits. A slightly weaker field can allow comets to remain bound for longer periods. The pattern of comet influx into the inner solar system could therefore depend on which side of the disk the solar system is moving toward. All of this leads to a startling realization. Earth's geological, climatic, and biological history is intertwined with the structure of the galaxy above and below us. For billions of years, the solar system has bobbed up and down through these layers. Each crossing left potential fingerprints, radiation shifts, dust influxes, comet perturbations, or interstellar interactions. Some of these fingerprints may appear as extinction events. Others may show up as evolutionary bursts, climate shifts, or geochemical anomalies. The galaxy above and below is not a passive void. It is a dynamic landscape that has shaped us, influenced us, and will continue to influence us long after humanity is gone. What lies above and below the solar system is not an academic question. It is a story of our past, our present, and our future. If we truly wish to grasp why what lies above and below our solar system could transform everything we think we know, we must go deeper still, beyond the magnetic scaffolding, beyond the hot halo, beyond the interstellar clouds and ancient shock fronts. and into the domain where the galaxy's grandest structures intersect, where cosmic filaments, galactic fountains, merging streams, and invisible gravitational currents converge into a vertical architecture that both sustains and reshapes the Milky Way over billions of years. This architecture is not fixed, it evolves, it breathes, it moves, and the solar system, drifting through it, experiences an environment far more dynamic than the simple flat disk model of a textbook galaxy would ever allow. To begin unraveling this deeper picture, we must consider the concept of galactic circulation. Not the circulation of stars around the galactic center, though that is important, but the circulation of gas, dust, magnetic fields, energy, and cosmic rays in vast, convecting loops extending tens of thousands of light years above and below the disk. This circulation is sometimes called the Milky Way's weather system, a system powered by supernovae, sustained by gravitational collapse, shaped by dark matter, and regulated by magnetic tension. Above the solar system lies one branch of this circulation, rising plumes of hot gas driven upward by supernovae in the spiral arms. These plumes expand into towering columns, their interiors heated to millions of degrees. As they rise, they stretch magnetic field lines, dragging them into the halo like ropes pulled upward by a weight. At the same time, the rising gas entrains dust, electrons, and ions. Some material cools and falls back toward the disk. Some escapes entirely into the circumgalactic medium. This is the galaxy's exhale. Below the solar system lies the other branch, in falling streams of gas that began far above the disk, but eventually cool, lose pressure, and fall downward, pulled by gravity. These streams are often metal poor compared to the disk. They are sometimes remnants of ancient dwarf galaxies, or clouds captured from intergalactic space. As they descend, they compress magnetic fields, stir turbulence, amplify cosmic ray production, and feed new waves of star formation. This is the galaxy's inhale. Together, the rising and falling flows form a vast galactic fountain, a self-sustaining feedback loop essential to the Milky Way's long-term evolution. And the solar system moves vertically through this fountain. As it does so, it encounters regions dominated by different phases of this cycle: hot outflows above, cooler inflows below, and turbulent transition zones in the middle. This raises a profound question. How much has Earth's history been shaped by the galaxy's breathing? Consider cosmic rays, the high-energy particles created by shockwaves in the disk and accelerated further in the halo. The density and energy of cosmic rays vary depending on where the solar system sits within this fountain structure. Rising regions of hot gas may contain tangled magnetic fields that trap cosmic rays, increasing their local density. Falling regions may be less magnetically confined, allowing cosmic rays to stream more freely. The solar system encounters both environments during its vertical oscillation. Strong cosmic ray environments increase atmospheric ionization, contribute to long-term climate cycles, and potentially influence biological evolution by altering mutation rates. But cosmic rays are only one variable. Dust evolves differently. In rising regions, dust grains are often destroyed by collisions with fast ions in the hot gas. In falling regions, dust accumulates, joining cooler clouds and drifting inward. The solar system, moving from one layer to another, encounters different dust compositions and densities, variations that influence the heliosphere's filtration, the zodiacal cloud, and the amount of interstellar dust that reaches Earth. Such changes might subtly affect Earth's reflectivity, cloud formation patterns, or long-term climate cycles. What lies above and below the solar system also influences how much interstellar material flows into the heliosphere. At times, the Sun encounters low-density plasma, and the heliosphere expands dramatically. At other times, the surrounding plasma density increases, shrinking the heliospheric boundary. When the boundary moves inward, Earth becomes more exposed to cosmic radiation and interstellar dust. Geological layers on Earth may record these transitions, periods of higher cosmic ray flux, changes in isotope ratios, or sudden increases in unusual particles embedded in ancient ice or sediment. But the galaxy's vertical structure extends into even more monumental scales. To understand these, imagine the Milky Way embedded inside a cosmic web, a network of enormous filaments composed of dark matter, gas, and galaxies connecting across millions of light years. The Milky Way orbits not in isolation, but within one of these filaments. The orientation of this filament relative to the disk contributes to the asymmetry between what lies above and below us. If the filament entering the Milky Way delivers gas preferentially from one direction, the halo above the plane may differ in density or temperature from the halo below. This asymmetric accretion could explain why some measurements show hotter gas on one side of the halo and cooler gas on the other, or why some superbubbles extend farther in one direction. If more gas enters below the plane, it may produce stronger magnetic field distortion or more pronounced turbulence. If more gas enters from above, it may produce greater heating in the upper halo. The solar system's oscillation through these layers is not synchronized with the inflow and outflow cycles. Sometimes we rise into a region of active outflow. Other times, we drift into an area where falling material dominates. This mismatch creates cycles of environmental conditions that no ground-based observer would ever suspect. Over millions of years, these conditions leave subtle but real imprints on the solar system and on Earth. Yet even these enormous flows pale in comparison to the influence of galactic mergers, the titanic collisions between the Milky Way and smaller galaxies. These mergers occur sporadically, often tens or hundreds of millions of years apart, but their effects ripple for billions of years. The debris of these mergers can persist far above and below the disk. Streams of stars, tidal shells, dark matter remnants, and shock waves that reshape the halo. The vertical axis of the Milky Way is strewn with such remnants. Some are so faint they can only be detected by mapping the motions of thousands of halo stars. Others are more dramatic, like the Sagittarius Stream, a colossal loop of debris flowing around the galaxy. These structures distort the gravitational field, creating regions where the galactic tide strengthens or weakens. When the solar system moves through them, comet trajectories in the Oort cloud shift slightly. Over long periods, such shifts may influence impact rates on Earth. One of the most extraordinary aspects of these vertical structures is that they preserve the galaxy's past. Every stream, cloud, bubble, and magnetic arch is a relic of events that occurred before Earth existed, events that continue to shape our world today. The galaxy is not stable. It is dynamic, still settling from ancient impacts, still absorbing dwarf galaxies, still adjusting its magnetic fields, still redistributing angular momentum across the disk. But the greatest discovery of all may be the possibility that the distribution of dark matter above and below the solar system is far from uniform. Some models propose that the Milky Way's dark matter halo contains vertical ridges or feathers formed by repeated collisions and resonances. These vertical structures could create zones where gravity is slightly stronger or weaker. If true, then as the solar system oscillates up and down, it interacts with a gravitational environment that changes over tens of millions of years. These changes may alter the amplitude of our vertical oscillation, the timing of our plane crossings, or even the shape of the solar system's orbit around the galactic center. Such gravitational modulations could, in theory, trigger subtle cycles in cometary influx, radiation exposure, or even solar system stability. Though still hypothetical, the idea reveals how complex the interactions between the solar system and the galaxy truly are. Above and below us, the deeper we look, the more layers we find, not of emptiness, but of structure, not of silence, but of ancient flows, not of stillness, but of currents that carry the memory of events that occurred billions of years before the sun formed. Consider that as the solar system travels upward, it approaches regions linked to the Erosita bubbles, those enormous remnants of past activity in the galactic center. Their shock fronts may extend outward, farther than we realize, subtly influencing the magnetic environment thousands of light years away. And as we travel downward, we drift toward regions shaped by different historical events, influenced by different streams, different flows, different ancient collisions. In this sense, the solar system is like a ship sailing through the ruins of a long-lost empire, drifting between monuments, walls, and currents left behind by events older than the solar system itself, and every layer we cross holds potential consequences for life. Every shift in cosmic rays, every change in the heliosphere, every alteration to the galactic tide, every influx of interstellar dust, every encounter with a magnetic anomaly, every subtle gravitational ripple from a dark matter structure we cannot yet see. What lies above and below our solar system is the history of the galaxy, written in matter, energy, and invisible architecture. And as we move through it, we become part of that history, shaped by it, influenced by it, and eventually recorded within it. Above and below us lies the story of the Milky Way itself. If we want to understand why what lies above and below our solar system might change everything we know, we must reach the outermost boundary of this journey, where the familiar meets the unknown, where our models begin to falter, and where the galaxy reveals its deepest, most enigmatic structures. Up to now, we have explored the interstellar clouds, the magnetic scaffolding, the hot halo, the dark matter streams, and the colossal remnants of ancient cosmic violence. But there is still a final layer, one that is not merely physical, but conceptual. A layer where the very idea of a solar system becomes uncertain. A layer where gravity, motion, and cosmic structure interact in ways that challenge our assumptions about stability, identity, and belonging in the universe. This final layer begins at the tidal truncation radius, the ultimate boundary of our solar system's gravitational domain. Beyond this point, the pull of the galaxy exceeds the pull of the sun. Objects wandering past this threshold no longer belong to us. They become citizens of the Milky Way as a whole. This boundary, located somewhere between 100,000 and 200,000 astronomical units, is not a wall, but a limit, a gravitational frontier defined not by what the sun can hold, but by what the galaxy can steal. As the solar system oscillates up and down through the Milky Way, this boundary shifts, slightly, subtly, yet significantly. A stronger galactic tide shrinks it, a weaker tide expands it. Pass near a dense stream of stars, and the limit tightens. Drift into a quieter region of the halo, and it loosens again. Over billions of years, these shifts carve away the outer Oort cloud, stripping comets from the sun's realm and sending them drifting through interstellar space. Some may eventually be captured by other stars. Some may wander alone forever. Some may fall into galactic currents that carry them far beyond the Milky Way. This constant sculpting of the solar system's outer boundary is not simply poetic. It has practical consequences. It affects the size and shape of the Oort cloud. It influences the rate at which comets return to the inner solar system. It determines which objects remain bound to the sun over geological time. And it defines, in the deepest sense, where our solar system ends, not in terms of light or wind or magnetic fields, but in terms of gravity itself. Above and below the solar system, the structures of the galaxy exert their influence on this gravitational frontier. Dark matter clumps warp it, stellar streams tug on it, passages through the galactic plane squeeze it, encounters with interstellar clouds push against it like waves crashing against a ship's hull. Over time, these interactions may even reshape the architecture of the Oort cloud, redistributing comets, destabilizing some, and stabilizing others. To understand this in full, we must consider that the solar system's vertical motion does not occur in isolation. It is part of a broader cosmic choreography involving the spiral arms, the galactic bar, the halo, and the dark matter distribution. Each of these components affects the gravitational field the solar system experiences. Each influences the tides, the forces, the flows that act on distant objects. Even the sun's orbit itself is not fixed. It changes gradually due to gravitational encounters and the large-scale structure of the galaxy. Over hundreds of millions of years, the sun's path slowly migrates inward or outward, crosses spiral arms, and shifts relative to the galactic bar. These larger motions combine with the vertical oscillations to create cycles so vast, so slow, and so deeply intertwined with the galaxy's evolution that they reshape our entire perspective on what the solar system truly is. The solar system is not a static bubble drifting through a static galaxy. It is a dynamic, evolving system embedded in a dynamic, evolving environment. And as the environment changes, the solar system changes with it. Consider the role of spiral arms. Though often portrayed as stationary swirls of stars and gas, they are in fact density waves, regions where matter piles up as stars orbit the galaxy. These waves rotate more slowly than the stars themselves. When the solar system passes through a spiral arm, It enters a zone of heightened star formation, increased supernova frequency, denser interstellar clouds, and stronger magnetic fields. This means more cosmic rays, more shock waves, more turbulence, and more radiation. It may also mean greater dust inflow, more frequent heliosphere compression, and increased perturbations to the Oort cloud. Now consider that the spiral arms are not symmetrical above and below the disk. Some extend farther upward, forming arcs that reach into the halo. Some tilt slightly, sending shock fronts into the upper or lower galactic regions. Some produce superbubbles that breach the disk more strongly on one side than the other. If the solar system crosses one segment of a spiral arm from below, it may encounter different conditions than if it crossed from above. This asymmetry challenges the simplistic notion of periodic spiral arm crossings and suggests that the vertical context of these crossings matters just as much as the radial context. The galactic bar, a massive elongated structure at the Milky Way center, also influences the vertical forces above and below the disk. The bar is not static. It rotates, it vibrates, it pulls on stars, gas, and dark matter throughout the galaxy. Recent models suggest that the bar may induce vertical waves in the disk, creating a corrugated, rippled structure that extends far above and below the galactic plane. Some of these ripples have been detected through precise mapping of stellar motions. These vertical waves propagate outward like the ripples in a pond after a stone is thrown. The solar system is not exempt from these waves. It rides them. As it ascends or descends, it may encounter regions where the disk is locally bent upward or downward. These bends may subtly shift the gravitational environment, alter relative velocities, or modify the path of stellar streams. They also hint at an even deeper truth. The galactic plane itself, the reference frame we use to define above and below, is moving. This realization means that the concepts of above and below are not absolute. They are temporary reference points tied to structures that are themselves dynamic. The disk breathes, ripples, twists, and slowly tilts over cosmic time. The halo shifts. The bar rotates and distorts the central mass distribution. The dark matter halo may precess or wobble. The entire galaxy is alive with motion, and the solar system is embedded in this living structure like a leaf drifting through a three-dimensional river. As we reach the outermost layers, we must consider the cosmic web, the filamentary network of matter that forms the skeleton of the universe. The Milky Way is part of this web, and the filament in which our galaxy resides may have its own vertical structure. Gas flows into the galaxy along this filament, supplying the fuel for star formation. These flows are not symmetrical. They may favor certain directions depending on the orientation of the filament. If more gas enters the galaxy from above, the upper halo may be denser and hotter. If more enters from below, the reverse is true. This asymmetry could influence the galaxy's magnetic field, its star formation rate, its halo temperature, and the distribution of dust and cosmic rays. It could even create a persistent difference in the environments above and below the solar system, a difference that alters our vertical oscillation cycles in subtle but important ways. As we zoom further out, to the scale of the local group, we see that the Milky Way is not drifting alone. It is moving toward Andromeda at hundreds of kilometers per second. The gravitational pull between these two galaxies creates tides that extend far into their halos. These tides stretch the dark matter distribution. They influence the flow of gas. They shape the gravitational landscape in which the solar system moves. And though the merger of the Milky Way and Andromeda will not occur for billions of years, the tidal interactions are already happening. Some scientists believe that these interactions may contribute to vertical distortions in the outer halo. If true, then even the distant gravitational relationship between galaxies influences what lies above and below our solar system. Still, the most profound implication of all is this: the environment above and below the solar system may hold clues about the origins of life. Consider that life on Earth depends on stable climates, consistent radiation levels, and a delicate atmospheric balance. Over billions of years, these conditions have been influenced, not only by Earth's internal processes, but by the galactic environment, the cosmic ray flux, the dust inflow, the compression of the heliosphere, the tidal perturbations of the Oort cloud. All of these may have played roles in evolutionary pressures, extinction events, and climate cycles. If what lies above and below changes, life as we know it might evolve differently. Other planets, other systems, other civilizations, if they exist, may also be shaped by their vertical journeys through their own galaxies. Perhaps some worlds rise into violent halo regions that sterilize them periodically. Others fall into dust-rich layers that blanket them in interstellar particles. Some may thrive in stable zones, some may perish in turbulent regions. This perspective reshapes how we think about habitability. It suggests that a star's location above or below its galactic plane could determine whether life emerges, evolves, or goes extinct. It means that galactic geography matters just as much as planetary geography. What lies above and below our solar system is not simply space, it is a dynamic ecosystem of cosmic phenomena, each one shaping the sun, the planets, the comets, the radiation environment, and, ultimately, life itself. To understand the future of the solar system, we must understand the environment we are moving into. To understand the past, we must reconstruct the environments we have already passed through. To understand our place in the universe, we must look not only outward, but upward and downward, because above and below us lies a story billions of years in the making, and we are only now learning how to read it.